Hello, my name is Matthew Vincie. I am an assistant professor in the Electrical and Computer Engineering Department at the Air Force Institute of Technology. In this presentation, I will be discussing some of the challenges associated with measuring sub-nanoamp currents during secondary electron emission measurements. In this presentation, I will provide a brief introduction to secondary electron emission for those with no prior experience. I will then discuss some of the shortcomings of current secondary electron yield measurements. Next, I will discuss some of the common techniques for measuring secondary electron yield. This will be followed by the introduction of the circuit model for our measurement system, and a discussion of our experimental data and our conclusions based on these results. Lastly, I will touch on our continuing research in secondary electron emission. In the phenomenon of secondary electron emission, a primary electron strikes the surface of a material releasing secondary electrons. In secondary electron yield measurements, we are interested in the ratio between the number of secondary electrons leaving the surface and the number of primary electrons impacting the surface. This is measured by taking the ratio of the currents associated with each. In 2005, Lin and Joy examined over 80 years of SEY measurements and found large discrepancies between measurements for even common elements. This is a plot of SEY versus primary electron energy for aluminum using the data compiled by Lin and Joy. The large range of possible SEY values for each primary electron energy may be caused by differences in the sample's surface composition, the design of the apparatus involved in the measurement, and the measurement procedure. More recently, we experienced our own problems when attempting to make measurements on the same material at two separate labs. In this plot, we have the SEY versus primary electron energy for a sample consisting of gold deposited on silicon measured by the two labs. This discrepancy required us to only compare measurements acquired at the same lab. We were able to gain valuable information regarding the relative change in SEY for different samples, but we cannot be confident that we measured the true or absolute SEY. Currently, no standard exists for SEY measurements, and it is difficult to determine which measurement apparatus and procedure is the most accurate in order to devise a standard. Inaccurate measurement results may bias simulations that employ SEY models calibrated using experimental data. The discrepancies found in SEY measurements hinder scientists from better understanding the secondary electron emission phenomenon. Very little research is available regarding methods for determining the accuracy of SEY measurements. Joseph Wang and others studied the effects that their measurement apparatus had on SEY measurements by comparing their measurements against particle and cell simulations. They computed a theoretical accuracy of 4% for a primary electron energy of 1000 eV that decreased to 20% at 5 eV. We are following a similar path in our research for determining the accuracy of our measurements. This presentation and the accompanying paper discuss the early parts of our research investigating the transient effects associated with SEY measurements. In principle, SEY measurements are made using an apparatus similar to that shown on this slide. There are 4 equations for estimating the SEY if the apparatus is capable of measuring all the current shown in the diagram. Note that the arrows are pointed in a direction opposite of electron movement, following the conventional current standard. Most apparatus are only capable of measuring 2 of the 3 currents, and some can only measure the sample current, requiring the sample bias to be varied between positive and negative voltages. Our apparatus was only capable of measuring the current through a Faraday cup and the sample. The Faraday cup was moved under the electron gun to provide measurements of the primary electron current and then moved away in order to allow primary electrons to strike the sample. Our system was designed to take measurements periodically in order to allow us to determine the transient effects associated with the measurements. Our measurements frequently involve currents of a few picoamps, which requires increased consideration when devising a circuit model. In this diagram, the voltages VF and VS are associated with the power supplies used to bias the Faraday cup and sample, respectively. The currents IS and IF are measured by two Keithley electrometers. The two voltage sources highlighted are the voltage burdens associated with the electrometers. And the highlighted current sources represent the input current bias of the electrometers. The two highlighted features represent the coaxial cables between our electrometers and the vacuum chamber. These transmission lines have associated resistance and capacitance that requires you to wait an extended period of time whenever changing the voltage on the power supplies. These plots show the currents IS and IF following a 100 volt step input at time equal to 0. If we zoom into the highlighted region, we see that the currents stabilize after approximately 1 hour. These long settling times had to be considered when devising our measurement procedure. Furthermore, the current through the transmission lines had to be minimized in order to mitigate the charging and discharging of the line capacitance. Next, let's take a look at the capacitive coupling between the electrodes in the electron gun and the Faraday cup. Changes in the potential of the electrodes within the electron gun would result in variations of the current IF through the Faraday cup. This is caused by the capacitive coupling between the electrodes and the Faraday cup. Based on this knowledge, our test plan incorporated a 30-second waiting period following changes to the potentials of the electrodes. Our measurements also indicated that capacitive coupling existed between our sample and the Faraday cup. This plot shows a transient in the current IS following a 100 volt step input on the Faraday cup circuit. Ideally, the free electrons would enter our circuit at the Faraday cup and sample. However, we have found that the electrons spread throughout the vacuum chamber and entered the circuit at undesired locations. The current associated with these electrons are represented by the highlighted current sources. Our vacuum chamber has exposed dielectric materials throughout. These materials are not located in the vicinity of our sample, allowing the electric field within this area to be controlled by applying a bias to the surrounding electrodes. However, the electric field surrounding the undesired location of electrons entering the circuit cannot be precisely controlled due to the presence of exposed dielectric material. In the plot shown, the current IS experiences 4 jump discontinuities. 3 of the jump discontinuities are due to the movements of the Faraday cup. The 4th is an unanticipated jump in the current. We believe this jump discontinuity is due to dielectric breakdown caused by charge buildup on the dielectric materials. This leads to a rapid change in the electric field and current flow in the previously mentioned undesired locations. These jumps in current were observed in both the currents IS and IF. As we continued measurements, these unexpected jumps would become more frequent and resemble burst noise. The phenomenon is enhanced by the rate at which the chamber is exposed to electrons and the duration of the exposure. We found that operating at low currents and switching the electron gun off between measurements allowed the charge buildup on the dielectrics time to dissipate, and we successfully performed measurements over periods greater than 24 hours without any unexpected jumps appearing in the data. This plot shows the current IF over one acquisition period. The period would begin with the electron gun disabled, and the Faraday cup beneath the electron gun. Then the electron gun would be enabled. Next, the Faraday cup would be moved away from underneath the electron gun. Finally, the electron gun would be disabled. The red boxes indicate the locations we extracted data from for further analysis. Data was extracted from points where it appeared that the signals had reached a steady state. Since all our equipment was driven by the same timing source, we were able to extract data from the same location in every acquisition period. By avoiding the transients, we were able to make measurements using currents as small as 140 femtoamps. Due to the noise associated with our system, measurements at a lower current were impractical. By programming our system to avoid these transients, we've been able to reliably perform measurements over periods lasting days. Our continuing research focuses on increasing the agreement between experimentation and simulation. Our simulations show that the primary electrons will arrive at the sample at various energies and at various angles. This is especially pronounced at low primary electron energies. We have developed a regression algorithm that combines simulated primary electron distributions against a large number of experimental measurements taken under differing conditions. This algorithm provides estimates of the SCY for different incident angles and energies. Our research continues to focus on primary electron energies below 100 eV, where measurement accuracy is more difficult to achieve. Thanks for watching, and I look forward to your questions.